This is the second part of the machine learning part 2 labs. Yesterday, we covered up to doing the business end of classifiers, keeping costs down. I'll just summarize that briefly so that we don't lose track of where we were. The key idea here was that any metric you use to understand a classifier should basically be consistent with the business function that the classifier is intended for. And to do that, we have a cost matrix, which you can see over here, which tells you what the costs of the various possibilities are: true negatives, false negatives, true positives. And you put that cost matrix together with the confusion matrix to calculate the average cost, which is expressed in this formula over here. And you find the average cost for different classifiers. So we quickly looked at two different very simple classifiers. The first one was the example in which we assume that no customer is going to leave our telecom company and go to another one, and so we actually don't send them any offer. And when we do that particular calculation, we find that the cost is $141 per person. And then the completely opposite end of it is we assume that all our customers are going to leave, and therefore we send everybody an offer to have them stay with us. And clearly, sending everybody an offer is kind of expensive. That costs us more money. So the point out here is that if we are going to write a classifier, we ought to be beating this number. If we don't beat this number, we might as well go home, right? We're not doing our job. So let's try a classifier. And because in the context of this lab, I don't really care about how good a classifier is. I'm not going to do any cross-validation or anything of that sort. I'm just going to have a very simple default classifier. This is the Gaussian naive-Bayes classifier. We'll talk about naive-Bayes later in the semester, but just think about it as a black box over here, right? So we're going to instantiate the black box classifier here. And once again, we're doing it in our doClassify function. And we're using the churn mask to see what we do over there. And we run the classifier, and we have a prediction. As you know now, the accuracy means nothing. The confusion matrix is kind of important, though, because it tells us that, remember that this is an asymmetric situation where there are many more negatives than there are positives, that there's an equal sort of asymmetry on both sides in false positives and false negatives. And we can predict on this classifier using the predict function here, and look at the confusion matrix, which was also printed up, and see what the average cost was. Using our average cost function. And we find that the average cost is $114, which is definitely less than, I think, the 140 number that we had to beat. So already, just by doing a very simple classifier, we're doing a better job. And so that's kind of hopeful. So remember over here, I'm using predict out here. And one of the things is that if I'm using an SVM, for example, there are no probabilities. And because there are no probabilities, I can't give you. I can give you these numbers over here in the confusion matrix, but I can't give you individual probabilities for each one of these. And the ROC curve is something that's actually kind of useful for this, as we talked about in the last in the last session, because all the ROC curve needs is basically something that you can threshold on. And SVMs do give you a decision function, and you can threshold on the decision function to do this. So let's, without much more talk, let's just go to the ROC curves. And we talked about how ROC curves work yesterday. And before we do that, we'll just very quickly talk about prediction thresholds, right? And we sort of talked about this yesterday as well when we were talking about this perspective of a cancer doctor. If you're a cancer doctor, you want the probability of having cancer to be extremely, extremely low before you say a person has cancer. You don't want to make it the usual 0.5. If you make it the usual 0.5, you might be killing a lot of people. You want it to be like 0.05 or something of that sort, because then you're like, okay, there's a very, very low possibility you have cancer, but there is a possibility you have cancer, and therefore you ought to go get a biopsy. So before we get to the ROC curves, we'll very quickly look at this reprediction that we can do. And what's happening in this repredict function over here is that if I have a classifier that gives me probabilities, I can use these probabilities. That's the probabilities of the zeros, and that's the probabilities of the ones, as we know from the last lab. and make a prediction whenever the probability of getting a 1 is greater than a certain threshold t. And if that's the case, we're going to predict it as a 1. So for example, in the cancer case, you might want this to be some really small number as 0.05. So you can look at what happens if I repredict with a number of 0.3 in here, basically. And you see that I make my cost is 106.95. And let's compare that to the previous cost, 114. The previous cost was higher. So by changing my threshold to something like 0.3, I actually do a better job. So this is this kind of rough idea. Of course, now you got to figure out what the threshold is, right? So we can just look at the probabilities. This is the probability of getting a 1. And you can see that in our sample, most of the things are negative, so the probability of getting a 1 is extremely low. 0.5 is what the standard predict function would do, and 0.3 was where we were. So, and of course, the reason we want to do this is we don't want any false negatives, because false negatives are costly. False positives are not so costly. So what the hell? We'll just get some more along this. We'll take some more of those samples. So at the 0.3 threshold, we make more money. So we do need to change the threshold in this asymmetric cost situation, but we need to figure out what threshold this is. So what we can do is now we can go to the RRC curve and make this RRC curve. Here's the code to make the RRC curve, and you'll see this on your homework as well. I'll just very quickly kind of go over this code. I didn't go over this code the last time when we talked about RRC curves in the lab, but the code is actually fairly simple. It uses the scikit-learn function RRC curve, basically, which pops out for you a bunch of false positive rates, true positive rates, and thresholds based on how an RRC curve is formed, which we talked about last time. It gives you the AUC, the area under the curve. And basically, it plots, and there are some properties of how this function is written. There is this skip over here, which says how many of the points in the RRC curve you should plot, and I did that because otherwise there's so many points that it kind of looks really very messy and too many points on top of each other. I also have something which annotates the thresholds for you on it, so you can do that as well. And there is this thing called label over here, which tells you how many of those skipped things you should actually be labeling. So make sure that you don't have labels all over the place. You'll be adjusting these in your homework, so I thought it's kind of good to go over them. And over here there is a name, which is the name you want to associate with the classifier, and that's used to basically, I think, set a legend for this classifier. And I think you can see that over here in this label up there. Let me just move this a little bit so that you can see it. And it's basically saying it's an RRC curve for that particular name. Okay, so that's what this function looks like. And I'm going to call it here. And I'm going to do a make RRC on the Gaussian naive-Bayes classifier, calling it GNB. That's not a particularly useful name, but that's okay. An important thing, this non-IPAS in here, that's for the axis. Its default is none. But the reason I have an axis argument in here at all is that I return the axis from this plotting function, and by returning the axis, I can put two of these together, as you shall soon see. So this is the RRC curve, and I have various thresholds printed out on it. And you can see what happens as you change the threshold from 1 all the way off to 0. First, you increase the true positives, as we talked about last time, and then you increase the false positives. And there is some spot over here, which is probably the spot your classifier wants. But how do you figure out that spot? That's what we're interested in. Okay. So now that we've an RRC curve, we need to figure out how to pick out the appropriate threshold. So while we're doing this, let's also just run another classifier, basically, to sort of do this classifier comparison. And then we'll use this method to pick out the threshold, actually to pick out a high-quality classifier for us. So here's an example of a decision tree. Verena talked about decision trees in Thursday's lecture. So we're just going to do a very simple decision tree. And here we set up a decision tree classifier. We reuse the training and test sets from the last time, and we run our decision tree classifier. The only parameter that we're going to mess around over here in the decision tree, there are other parameters that you can set, but we're just doing this for the sake of understanding classifier comparison, not to understand decision trees. So I'm just going to change the depth of the tree and let that float from 1 to 10. Okay, so we do this whole thing, and we have some decision tree classifier. And now we're going to compare these two, and We're going to compare these two on the ROC curve. You can quickly see the confusion matrix. It seems to have far less. The other one had 80 and 80. It seems to have far less of these, but it seems to have many more, as you can see, false negatives over here. Okay, so we compare these. You would use make ROC, and you return the access from it, and you use that in the next one. And you can see these two classifiers here. This is the naive Bayes over here, and that's the decision tree. And you can see the decision tree is much better at the beginning. It actually gets a lot of true positives here, and then it starts bottoming out. It actually becomes less high than this one. And the area under the curve for the decision tree is slightly higher because of all this stuff in here. So overall, you get some kind of vague notion that a decision tree is perhaps a slightly better classifier because because the area under the curve is 0.87. But this is not strictly a true statement. The strictly true statement is you have to ask the question as to where in this ROC curve you're looking. So, how do we read which is a better ROC curve in this scenario? The usual advice that people will tell you is that go to the northwest corner, and you go to the northwest corner because you're at the 1.0 over here, and at the 1.0, you have no false negatives. You have no false positives, and you have all true positives. But remember, this is not our aim in this classifier. This is an asymmetric situation. We want to minimize as many false negatives as possible. We'll tolerate some false positives. So it doesn't necessarily mean that we want to go here, but we might want to go somewhere here or something of that sort. So let's look at that in a little bit more detail. Okay, and we'll come back to this very soon. But we've been talking about cost so far, and suddenly in these ROC curves we've stopped talking about cost. So let's go back to talking about the costs of these various classifiers. Okay, so we're going to do reprediction again now with this cost or risk. So I'm going to skip over a lot of this decision theory math, but I'm going to sort of talk a little bit about some of the philosophy behind this thing over here. So when you run a classifier like logistic regression or the SVM, there are actually two losses. We've sort of hinted at this in earlier labs, but there are two losses you need to think about. The first loss is the one you use to train the classifier. For example, when you do a logistic regression, there's a probabilistic model behind the logistic regression, which has been talked about 2 labs back. And this probabilistic model is what we are training for. It's basically a maximum log likelihood model. And we're trying to find the parameters of this probability model. So that's what I like to call the estimation risk. So that's one part of it. Then there's a second part of it, which is this decision-making part, which is the part which is done typically in the cross-validation folds, or which is done on the test set here, and where we're trying to make a decision whether something ought to be a 1 or whether something ought to be a 0. Is this person going to churn, or is this person not going to churn? So that risk is a different thing, basically. As I said, if you're a cancer doctor, with even a very low probability that a person has cancer, you want to say that the person has cancer so that you can take some action. Similarly, as a company, if you have this slightest notion that this person is going to bolt from your company to go to another company, you want to address that. And so the decision theory depends upon the business situation. And so the risk is different. It cannot be the same risk as estimating the probability, right? Because the probability is what it is, and your decision is different based on different thresholds of the probability. So I'm going to skip over the math, but you can basically show, roughly speaking, and why is it roughly speaking will be talked about a bit later in this class, that your threshold must be R divided by 1 plus R, where R is this particular ratio of false positive minus true negative and false negative minus true positive, the costs of these things. So you can see, let's assume for a second that it's not true in this problem, but just let's assume it so that we can actually understand that the true negatives and the true positives cost nothing. Then this ratio is the ratio of the cost of false positives to the cost of false negatives. What happens under this situation? Suppose the cost of false negatives is much higher, as is true in the cancer problem or as true in this churn problem. Typically, you're going to find that this denominator is going to be much higher. Since the denominator is much higher, this number is much smaller than 1. And if this number is much smaller than 1, basically, so for example, let's say it's 0.2 for the sake of argument. So this is like 0.2 divided by 1 plus 0.2, which is even less than 0.2. It's like 0.18 or 0.17 or something of this sort. So that's telling you that the probability threshold should be like 0.17 or something. And that kind of jives, this math kind of jives with your intuition that you needed to reduce that probability threshold. We can do this calculation here for us. So we have this cost matrix, and I can calculate in this function rat this the ratio from this cost matrix. And I can repredict actually based on that, and I'm going to print it out over here while I repredict it. So here, I'm going to repredict based on this threshold, which is now calculated. You can see it in this line over here, which is now calculated from this ratio. That our ratio R is 0.22, and the threshold works out to 0.186. So it's roughly, it kind of makes sense with the intuition. And notice when we do this, that our cost has gone way down. It's gone all the way down to 98 from 106. So we even reduced the cost further. Remember earlier we tried for the 106, we tried at 0.3. Turned out we needed to go even lower. So you can actually plot this, and I actually plot this so for the decision tree. This also was for the decision tree. And you can see what it looks like. So here's the surface. So here's the threshold. And there is actually, in this particular case for the decision tree, there's a wide range of thresholds for which this will kind of work. If I was to do this, on the other hand, for the naive Bayes classifier, which I can just do by changing this here, I believe. It looks a little bit different. And you can see it's not exactly at 0.18, but the minimum is somewhere near. And we had that 0.3, it was 106, but at 0.26 it becomes even lower over here. So, again, all this reproduction, I'm using a probability. And I'm thinking about this in terms of probability. But remember that a SVM does not provide a probability, right? And there are other classifiers that don't provide probabilities. But they do provide us decision functions, and we can use those. And this is where, again, we want to go back to sort of this ROC curve kind of notion, because all the ROC curve needs is basically an ordered set of thresholds. And you can use the decision function basically as an ordered set of thresholds. Okay. So let's go back to the cost that we were talking about. So notice that the ROC curve has a very interesting property. That if you look at the confusion matrix, which I should have probably re-put down here, but I'm going to go up all the way until I find it. Keep going, keep going, keep going. The ROC curve has this interesting property. We talked about this last time as well, that it is only made basically using the observed ones. The TPR, the true positive rate, only comes from here, and the false positive rate only comes from here. And so it doesn't actually, it doesn't take into account the relative amounts of observed zeros and observed ones. In this case, remember, the observed zeros are much more. Keeping that in mind, it should be kind of obvious to you that the way that we actually kind of figure out things on the ROC curve actually does depend upon the imbalance, but there is something external we can do to the ROC curve to find this. And so what is this? Well, again, we're solving a business problem. Since we're solving a business problem, let's actually look at what we're trying to do. We're trying to minimize the cost. That's the function for the cost, right? That's the cost times the probability. And this estimation of the probability comes, as I said, from the confusion matrix, where you take the, this is a true positive, so this is the true positives divided by the total number. So you can write this thing out, and when you write this thing out, you can actually sort of take the, use the formula for conditional probability to write this out. And you can write this as the prior probability of having a 1 times the conditional probability of having a predicted 1 given that the actual thing was a 1, right? And so on and so forth. Each one of these terms can be split, basically, by using the formula for conditional probability. And so we get these, 4 parts, part 1, part 2, part 3, part 4, just like up there. But in part 1, we can take the prior probability of getting a 1 out, and in part 2, we take the prior probability of getting a 0 out. And when we do that, basically, you can see that this probability of having a 1 given, that's just the true positive rate. And the probability of getting a 0 prediction given a 1 actual is 1 minus the true positive rate, naturally. And so you can write this entire thing out in terms of the true positive rate and the false positive rate. I'll leave you to convince yourself about this formula. But once you do this, notice that you have a cost, which is given in terms of the true positive rate and the false positive rate. Now you know that a ROC curve is basically a line which is a true positive rate, it's a curve on the graph of false positive rate on the x-axis and true positive rate on the y-axis. So let's write it in those terms. So I'll rewrite this formula in terms of cost and false positive rate. I'll rewrite the true positive rate in terms of that. So it's just basically algebra, which I'm messing around with over here. And this is what I get when I do that. So there are multiple things that you should be able to note from this formula straight off the bat. Firstly, that if I keep cost constant, if I tell you that cost is a number, then this is the equation of a straight line. It's m times x plus b. So this is the equation of a straight line. Given that is the equation of a straight line, I can now say that curves of constant cost on the ROC graph are straight lines. Given that that is true, the slope of that straight line is that ratio r we calculated earlier, which was roughly speaking the false positive cost by the false negative cost, times the imbalance in our data set. So we have many more zeros here than we have ones. So that's the imbalance in our data set. That's our slope, firstly, right? So typically for a false negative case, right, you're going to have the r being kind of small, like 0.2 or something of that sort. But it's going to be somewhat mitigated by the fact that this ratio is of the zeros to the ones. And in a false negative case, typically you, in a more expensive false negative scenario, you typically have more negatives. You typically have less people who have cancer. You typically have less people who are going to churn. But the ones who churn are expensive, and the ones who have cancer, you want to get your prediction right. So overall, what happens is that this number is going to be less than 1, and this number is going to be higher than 1. And so it might just so happen that these cancel out and you get a slope of 1, and the whole northwest corner thing actually turns out to be an accurate way of doing this. But depending upon what the costs are and what the imbalance are, this number changes, and we'll see what it is for our case. So that's the first thing you should kind of note. The second thing you want to note is sort of this scenario. So actually, I think in these first and second things, I said all of these three things over there. So for the the second thing you should note, of course, is that for the balance case, when P0A is equal to P1A, it just depends upon this ratio R. And furthermore, if you're talking about a scenario in which false positives are equally expensive as false negatives, which is the usual scenario, it's just 1. So then you are actually looking at a line which is a line of slope 1. The question, of course, here is that which line are you looking for? And the answer I'm going to tell you is that you're going to look for a line which is tangent to the ROC curve. Why is this the case, that you want a line which is tangent to the ROC curve? Well, think about it. For that, you should go look at this formula here. Here is an intercept. If I want to have the minimum cost model, right, what do I need to do? Okay, so I want to have the minimum cost model. So if I have 3 different models, one of which has the lowest cost and the other 2 have slightly higher cost, this number, right, is going to be maximized, essentially, at the place where the cost is minimum. So if this number is maximized, then this entire intercept is maximized. So what you want on your curve is a line, basically, where the intercept is maximized. And you can see what happens if I do this, right? So here's a line. Here's a line. I find out, for example, let's take the situation where the r is equal to 1, and as well, and it's a completely balanced set. So the slope is 1. So you're drawing 45-degree lines. So you draw a line like this, boom, which cuts it at 2 places. But the intercept is so. The intercept is lower, which means the cost is higher. Then you do this one. Okay, the cost is a little bit lower, but it's not the lowest possible cost. Then you do this one. And then finally you come here, and that gives you the highest possible intercept. So the tangent lines are always going to give you the highest possible intercept. And therefore you want it to be a tangent line, because the highest possible intercept corresponds to the lowest possible cost, and that's what we're looking for. So that's the game. We're going to look at these tangent lines. Now we can go and look at this in the case of imbalances. For example, if I had a completely balanced set, but I had different costs, if I had a high R, then and you wanted to penalize false negatives, then you'd be over here, and to penalize false positives, you'd be out here. Okay. So one can use this tangent line method to find the find the classifier we ought to use, and multiple questions about the ROC curves get sort of answered. So for a balanced data set, what are these? For a balanced data set with equal misclassification costs and no costs for true positives and true negatives, the slope is 1, and we want the 45 degrees lines. The 45 degrees lines get us closest to the northwest corner. That's point 1. Okay. Classifiers which have some part of that ROC curve closer to the northwest corner than others have tangent lines with higher intercepts and therefore lower costs. So those are the two things. In any other case, you want to find the line. And let's actually go do this. So we can print the ratio of our cost, which is 0.22, and we can get the slope by looking at the ratio of this cost times the actual zeros divided by the actual the probability of actual zeros, the prior probability of actual zeros, and the actual ones over here. So I just take the actual zeros, the fraction of actual zeros divided by the fraction of actual ones. I could even do the numbers. I didn't because the denominator is the same. And I multiply these two, and I get a slope of 1.39. So which is a slope over here that turns out actually to be somewhat higher than than the slope of a 45-degree line, which may be a little bit slightly counterintuitive, because I was just telling you that you want to go into sort of like the into penalizing false positives here. But again, that's just sort of like this diagram here was only for balanced sets. The point out here is that the ratio was 0.22, but this ratio, the ratio of actual negatives to actual positives, i.e. people who don't churn to people who churn, I do not need that outside bracket, is 6.05, which is kind of basically overwhelming the 0.22 and giving us a 1.39, all said and done. Okay, so let's plot this line on this RSE curve. Here is the line on the RSE curve, which has the appropriate slope that we're talking about. And I've used IPython Notebook's little intercept thing, so we can actually change what this intercept is. So I can move this. And you can see that I'm moving the intercept up. And as I move the intercept up, I get more and more tangent. So first let me go on the Gaussian knife base curve to find the tangent to that curve. Coming close, coming close. Boom. There, roughly. That seems to be the tangent point. So I can see that the intercept out here is something slightly less than 0.5. And I can use this intercept to basically calculate the cost. And I'm going to get some cost. But notice that the intercept for the green one, which is the decision tree, is even higher. And thus the cost is even lower. So I can find the intercept. From the intercept, I can now calculate the cost for you. And boom, we're done. This is the model we want to use, because this model has a lower cost. Okay, so I'm being a little bit glib about this, but from this kind of analysis, it tells us which model we want to use. But this is not all that goes into a business analysis, and this is why I said I was being a little bit glib. And we'll come to that in the next step, where we talk about cost curves. But if I had an infinite amount of money, this would be the answer to my this would be kind of the answer. I don't have to worry about budgets and so on and so forth. Or actually that's not a really precise statement. The precise statement I'm trying to make is that if I had a certain amount of money, then this model has lower overall cost because the intercept is out to the left. But let's make cost curves, and you'll see that there is a slight. I need to qualify my statement a little bit. So what is a cost curve? So a cost curve is an idea which is just like the ROC curve, but just slightly different. Here's the basic thought behind it. What I want to do is I want to plot the cost with the percentage of my samples that are positive against this, the percentage of my samples that are positive. So what's going on? Remember, we are going down the thresholds from 0.99, 0.98, 0.97. Let's think about this in terms of probabilities again, even though we actually don't need to do it in terms of probabilities. All the way down to 0. At a threshold of 0.99, as we talked about yesterday, you may just get one sample positive. And as you keep lowering that threshold, or as you keep making more and more samples positive, depending on how you do your RSE curve, you are making more and more true positives, and then more and more false positives, and you're going down this list. But the point is you're making more and more things positive. The key observation is that the first few samples you get out, right, when you do this, if I take only the top 10% of these samples, then these top 10% of the samples are the ones most likely to be positive. Those are the ones which even sort of like broke through the 0.98 or 0.99 barrier. This is something that has a probability of churning greater than 0.98. So this is an almost certain churner. So if I calculate at every threshold the percentage of people who are going to churn, then at lower percentages, I am getting the absolutely short churners. And those are the folks, from a business perspective, I absolutely need to target. Those are the people I need to target first, right? So let's calculate this. Let's do this for every threshold, and let's find these percentages, okay? And then what we're going to do is that we are actually going to find the average cost. So here I've defined this average cost 2 function, which writes for me this cost in terms of these true positive rates and false positive rates we saw earlier, and which we used to make that line that we drew on the ROC curve. And here I calculate the percentage, which you can convince yourself comes from this formula over here, of folks who are, who are the most likely to be positive. And then I'm going to plot the cost against this percentage. Okay, this function is very, very similar to the ROC curve function, and definitely also uses the ROC curve from sklearn. Okay, so let's do this. We plot this. This gives us a very interesting graph. Firstly, it tells us what we already kind of knew, that the decision tree actually achieves a lower cost over here. And the Gaussian Bayes does not actually have that lower cost. That's the first thing. Notice I've also sort of labeled the thresholds on this. And so you can see that this low cost over here comes at a threshold of like 0.22 something, and the threshold is similar over here. It's like 0.25 or something of that sort. That's the first thing you should notice. The second thing that you should notice, basically, that if you only had a finite budget, right, over here, things sort of change. So let's assume for a second that yeah. So here's sort of like my analysis of this. There's a cost associated with targeting predictive positives, right? The cost can be read off the graph above. So say we had 1 million customers, okay? And I can target, and say I decide I want to target only 10% of these customers. So let me go to this 10% spot, because obviously I want to target my most likely 10% churners. So let me read off this. At 10%, I can go to, I have 110 on this curve, and I have a cost of about 120 on this curve. This is going to save me money, basically. So if I have a budget, so if I have, so at 10%, if I have 1 million customers and at 10%, that becomes 100,000 customers, essentially. That means I'm talking about a sort of like a minimum budget at 100,000 customers of $10.3 million, right? Because I'm talking of a budget of like $10 million. So if my boss came to me and my boss told me that you only have a budget of $10 million, then I would go to my boss and say, okay, with that budget, reading it off this curve, it's sort of between 110 and 120. There's only about 100,000 customers I can target, and these are the customers I'm going to target. And furthermore, I'm actually going to use the decision tree over the Gaussian Bayes classifier to do this targeting, because it's actually saving me $10 per person. And on 100,000 customers, $10 per person is $1 million. That's $1 million in savings right there. Okay. But now your boss comes back to you and says, yeah, we have a lot of money. We don't have a budget of $10 million. We have a budget of, let's say, $60 million for this campaign of yours. So you say, okay, I have a budget of $60 million. Okay, that's 6 times more than $10 million, so I can target 60% of my customers. So I can go up this line, and I'm targeting 60% of my customers here. Of course, again, I'm targeting the 60% of them most likely to churn. And of these, clearly there's a lot of them who would not have churned anyway. So the cost is going to be higher. But at 60%, you see that the answer actually changes. You can see that the Gaussian Bayes basically, came like that, and at some point it switched over. In fact, it switched over at about maybe 30% or 32 or 33%. So even at 40% of your customers, or $40 million, you would say that if I had $40 million to run the campaign, I would use this classifier instead, because it gives me lower cost. So you might have said, on the whole, oh, but we did this ROC curve, and the decision tree classifier turned out to have the overall lowest kind of cost because of this line thing. And you're right, that is the case. But that answer corresponds to a particular threshold, which was picked out by the which was picked out by the cost analysis, right? But the threshold, what I'm trying to show you out here is that the threshold is not necessarily a fixed thing. It depends upon your business situation. It depends upon the amount of money you have. If you had only $10 million, then your threshold needs to be somewhere around here. But if you have $40 million, your threshold is over here. So This is how you actually use a classifier. So if somebody came and asked you the question, which is the best classifier? Well, the answer is it depends on how much money you have. What the ROC curve was telling you was it was comparing this bottom over here to this bottom over here. But that may or may not be the right question to ask. So, as always, and you know this from just common sense, ask the question, what are your aims? What is the aims of your business? You're a doctor. What do you want to do? What do you want to prevent? So those are the questions you should ask, and then go ahead and do an analysis, and you'll come with an answer. Thanks.